Hello, ladies and gentlemen. My name is Joshua, and it's my pleasure to welcome every one of us to an introduction to auto-regression distributed lag approach to cointegration analysis. Most economic time series are not stationary, as we all know. And the technique commonly used to overcome the problem is termed cointegration analysis. There are various cointegration approaches, including Engel and Granger, Philip Ulleris, Johansen, and of course, ARDL. For the first three, we may wish to watch my YouTube videos on the topics. Today, we want to look at ARDL approach. The ARDL is particularly useful when we have variables that are first difference stationary combined with some that are stationary at levels. It's also a very good model when we are sure that we have just one cointegrating equation. We may wish to read some articles that speak extensively on the methods, including the conditions, the limitations, and assumptions. The first I will recommend is Autoregressive Distributed Lag Modeling Approach to Cointegration Analysis by Pesaran, who developed the model. And the second I want to recommend is an out package for the analysis of level relationships. It's published in the Journal of Open Source Software and written by Asopoulos. One other one I want to recommend is, let me check for the last one I want to recommend, is published in Journal of Statistical and Econometric Methods by Nkoro and Nkong 2016. The topic is auto-regressive distributed lag integration technique, application, and interpretation. Let's start by loading necessary packages. Our interest will just be two packages. Okay, let me add another one, which is DLAGM, but we shall come across that later. So we need ARDL for estimation of the ARDL model. We have urcl for performing our unit root test. Now, for the data we want to use, the data is in my working directory, which is ARDL folder. So on my desktop, I have the folder here. So this N9G variable we want to use, let's import it. So here is the data set. So the first thing we want to do is to test for stationarity of the variables of interest. This is necessary because usually ARDL crash in the presence of second difference stationary variables. Let's check the names of the variables in the data sets. There are quite a lot of them here: country code, GDP per capita, openness, human capital, and a lot more. But our focus will just be 5 variables. We have the TFP, agricultural expenditure. Then we have openness, the human capital, and inflation. So we want to look at how those variables actually determine total factor productivity that we have estimated. And the TFP in this case is agricultural TFP for Nigeria. Okay, we will not find function URDF, so sorry, we have not. Let us go back and load the packages. So load them, run. Yeah, beautiful. And in case you don't have the packages, you can install them. Go to tools. This is tools up here. So tools. If you click on tools, then you will see install.packages. Then you just follow the instructions straight away. So let's check for stationarity of TFP. So for TFP, here is minus 6.39. At 5% is minus 3.50. 10% minus 3.18. So this is showing us clearly that the variable is stationary at level. Agricultural expenditure, the value is minus 4.03, stationary at levels. Openness for openness is not stationary. You can see the value is higher in value than even 10% critical value. So then we take the first difference and check for the unit root using augmented Akifuller test again. So here we are. So clearly, openness is first difference stationary variable. Then inflation. Human capital. For human capital is minus 3.38. So we extend it to 10%, that is still in order, stationary at levels. Then inflation is clearly, inflation is minus 3.97, clearly stationary at levels. So we have all the variables stationary at levels except openness, which is a first difference stationary variable. So the next thing is to determine the best lag order for different variables to be included in our ARDL model. By rule of thumb, for our auto ARD function in ARDL package, the maximum order is determined by rule of thumb by checking the log of the number of observations. And our observations run from 1981 up to 2018. That's about 37 years. We check for log of 37. That will give you 3.6, approximately 4. So that's how I got this 4444 here. So here I have my model. The data is NIG, the maximum order. I have 5 variables. So the lag orders I use. I use DIC selection criteria. You can use DIC or which other, any other one of interest to you. And generally, we know that the lag order to be selected as the best will be based on minimum BIC. So that's why I say selection of that's called min max. It's a function ARDL. So if we have done it correctly, so we can run this and check for the best order here. So the best order is 34344. 3 lag 3 for TFP, 4 for aggregate expenditure, 3 for openness, 4 for ECM, 4 for inflation. Now you may wish to look at other lags and to confirm that we have selected that one based on minimum BIC, see clearly. So we may wish to look at the summary of our ARDL model. So this is Sorry, let me know. Sorry, we have not run the model. We are looking for the summary. So run the model, beautiful. So let's check for the summary. So beautiful. So you can look at it carefully. So if you look at, let's check the results. If you look at the results here, you can see that the adjusted R square is fine, and the remainder of the variables are statistically significant. So now the next thing is to check for the band F cointegration test to ascertain whether cointegration actually exists. Yeah, so let's run it as band underscore F test. That's the function. So we run this. Then let's get the table. Yeah, the statistic is 15.12 here. And you can see it clearly that it's greater than the lower and the upper band. And given the p-value, it's actually showing us that we have co-integrating equation. So we want to quickly look at the long run since we are sure of co-integration. So we use multipliers, that's the function, to extract the long run model. So here, so we can clearly see that apart from openness, all the variables are statistically significant in the long run. So let us look at, then the next thing is, let's check for the residuals. So this, I call it ARDL L1. So I use case 3, this the case that includes the trend as well as the intercepts. Then get the summary. So the summary is, take note of this mean, minus 1.0437. We may wish to look at the plots for the long run relationship with the dependent variable and the fitted values of the model. And to do that, we use plot underscore R function. This is our model. This is the residual. So run it. And here we have the TFP. This is the fitted value. This is our ECT, which is the long run. So we move to the unrestricted ECM. The function is uecm, so that's you cater for all the variables. And run it. You can get a summary straight away. But more importantly, check the residual like before and get a summary for the unrestricted ECM. Check the mean again, minus 1.0437. Take notes. Since we have established co-integration, then we need to look at the restricted error correction model. So for the restriction error correction model, the function is recm. So we have the model, then and get the summary. So we look at summary here, go up. So this, then you can check for the ECT. The ECT is negative and significance. And check for the significance down there. That's beautiful. Yeah. So again, check for the residual. And again, get the summary. And take note of the mean, minus 1.0437. So you can see that the residual for the ARDL, the unrestricted ECM, the restricted ECM, identical. You may quickly wish to check for that there, because they're identical, then check for. So you can see. And the fact that the residuals are the same is another way to be sure that cointegration exists. So we may wish to look at a graph of our TFP against the residual of the restricted model. So in this case, I convert my TFP to time series run. Then I combine the two using cbind. Then I autoplot. Beautiful. You can see it's very, very clear indeed.